All right, we're going to start. If we could have everybody attending remotely to please close your microphones, it would be really great. So good afternoon, everybody. My name is Jesus del Alamo. I'm professor of electrical engineering. And this is another one of our joint Microsystems Technology Laboratories AI hardware program joint seminars. So we're trying to bring microsystems and AI hardware together. And today we have the pleasure of hosting Mike Davies from Intel, who is going to give this talk remotely. Mike Davies is director of Intel's Neuromorphic Computing Lab at Intel Labs. He holds degrees from Caltech, and he was a founding employee at Fulcrum, where he was involved in IC development for 11 years. At Fulcrum, he pioneered asynchronous design in industry-leading networking switches. Mike joined Intel in 2011 as part of the acquisition of Fulcrum Microsystems by Intel. And since 2015, his group in Intel Labs has been involved in brain-inspired AI processors, such as Intel's Loihi. And the title of his talk today is Making Computing More Brain-like. Mike, it's a real pleasure to have you with us today. Thank you very much.
Thank you, Jesus. And yeah, I wish I could be there in person, but thanks for the opportunity to give this talk remotely. To begin, why would we want to make computers more brain-like? And it's interesting to step back. Of course, there's been incredible progress that's been made over 7-8 decades of conventional von Neumann computing, and recent gains in AI, of course. But still, brains remain unrivaled in many respects. If you consider not even the human brain, but small brains in natures, things like a cockatiel parrot, and consider not just its ability to solve tasks that we today are looking at, like image recognition and navigation and control of autonomous flying, but this combination of all these capabilities all in one computing device at power levels that are orders of magnitude lower than what we have conventionally achieved today through all the progress in process scaling and whatnot. So a cockatiel can, fly around in completely unknown environments, navigating, finding food, finding mates, doing everything human or living organisms do. They can even learn, online, while it's behaving throughout its lifetime. It can learn things that clearly were not in its evolutionary training repertoire, things like learning human words, learning how to manipulate cups even for drinking. And this is an organism that can sit on the tip of your finger. And you compare that to what we've achieved, very recently, which is impressive, of course, autonomous drones, drone racing competitions that are held now at conferences like IROS. And, it's impressive. They're reaching human scale reaction times and speeds in navigating, these racing courses. But this is a highly rigidly constrained task where the flight paths are totally determined beforehand. There's no learning, there's no adaptation, decision making that's happening, in this embodied device. So great gains, yet still we are far from achieving, the advances in AI at the level that we can deploy it into, form factors that we might want to. So the neuromorphic computing vision is to really understand what is it about biological brains that give it this incredible speed of processing, efficiency of processing, versatility, and ability to adapt. And deploy that into conventional computing devices, into chips that we can build, systems that we can scale up. We find an incredible promise here of scaling, where you find brains in nature across all scales, everything from ant brains to human brains. And that's all with the same basic building blocks, the same neurons and synapses. The basic machinery is all the same. It has an incredible ability to scale across many orders of magnitude form factors, and that's a kind of scaling that we simply don't see in conventional computing. There's a whole difference in architecture and algorithms and software that you have to deploy in order to, say, build a supercomputer compared to building an edge CPU that would control a drone. So our aim here is to achieve large gains. So 10 to the 4, 10,000 times gains in energy delay product. That's kind of a target that we have in our group. We have examples that reach that level, and we think that as we understand this more with today's design tools, manufacturing technology, or at least emerging in the coming years, we will be able to achieve that quite readily. So as we look to neuroscience, kind of the modern understanding of how brains operate, we find a wealth of unfamiliar, exotic, very fascinating properties that we don't find in conventional computing systems. And there's really a spectrum of, some things which are, very commonplace. So, the use of low precision computing, of course, that is very well appreciated even from the earliest days of computing, all the way up to features that we're unlikely to be tackling and adopting for some time. So self-organized assembly and manufacturing, the biological growing, the organic growing of these systems. But there's everything in between, and this represents a very rich space of design exploration where we can draw inspiration into this design process. And of course, what that means is, we could spend decades just wandering through the solution space, but really we need an iterative architecture algorithms code design process. In conventional computing, AI is now, in recent years progressing so fast because the architecture that evolved for other purposes, so graphics, a rendering, happens to be very good for accelerating, certain algorithmic models, large matrix linear algebra based, high dimensional computing models, and that's eliminated one dimension of that optimization problem, and it's worked out very well. But really, if we look at this chasm that we have to jump, if we're going to actually achieve something like the form and the efficiency of biological brains, we really have to engage in the rethinking of all of those architectural hardware principles that have been around for decades now. And so that's what we're trying to do in my group. We're kind of rethinking all of those assumptions. We have followed a certain decision tree that's led us to the types of chips that we're researching, which happen to be all digital, for example. But we're doing that so that we can rapidly explore the algorithmic space, see what insights that provides back to architecture and to the chip design process. All of that is done through a rigorous benchmarking process so that we have confidence that we're moving forward and not just randomly walking. So some of the principles that we have found particularly interesting that we would term neuromorphic here are, for example, dynamics in the neuron models themselves. So this, in the conventional neural network models from, machine learning now that have become very standard, these are stateless models. These are very simple nonlinear functions that just sum up inputs and apply a ReLU function to that or some similar nonlinearity. Whereas biological neurons and the types of neurons that we're looking at implementing in hardware are stateful, and they're really their own little dynamic system. These equations governing their behavior here, shown on the right, it's a dynamical system, and there's there's time variables in there. So really, they're nonlinear filters, and which means that they fundamentally operate in time. And just right there, they offer an opportunity for efficient, time series data processing, because that's fundamentally how they're operating. And in addition, of course, biological neurons are spiking. They don't just continually output numbers all the time, or voltage levels. And that spiking behavior is sparsifying the communication, which has all kinds of benefits when you have to face the problem of interconnecting neurons like these. So that's another principle here, is that, if you think about these stateful neurons, how you might compute with them, where now the activation of a particular neuron is a moment in time. It's a point in time when that state variable in the neuron reaches some threshold or some condition where now it's active in some way, and you want to process that information. There's multiple ways you can go about identifying that and servicing that kind of an event. It turns out that asynchronous sparse communication is a fast and efficient way that offers all kinds of benefits. And this is what the brain does. It's a massive sparse network. It's asynchronously connecting or communicating all the activity of these temporal neurons. And this little kind of cartoon depiction here is just showing that supposing you have a collection of these neurons, you could also think of these as memory elements, state elements. If you're storing these in some kind of a mesh, an array of some kind, in a chip we might build. And if you have an asynchronous fabric, you have an asynchronous implementation here where the assertion of an individual neuron is immediately noticed by the interconnect and can be immediately sent where it needs to go, be that an axon to other neurons, or it's a memory, it's a communication channel or a memory interface, if that happens to be, in the system. Having that be asynchronously identified and communicated is going to be much faster than needing to service this array or this collection of neurons on some fixed interval, and then having to sift through all the elements that are not as active as the ones you're interested in, the most active elements. So temporally asserting activity, asynchronously identifying that and communicating it leads to gains in latency, energy efficiency, and this is architecturally, if you look at the brain, this is what's going on pervasively. So all of that, as well as other principles and properties I'm not going to go into, all of that leads us to what we see as a new class of computer architecture. So distinct from the von Neumann model, the standard computing model, distinct from data parallel models, modern, evolutions of that, which is, what we have in GPUs and providing great gains in AI today. Really, this is something different where you have a sparse assembly of neurons. Everything is communicating asynchronously, sparsely active in time, and every parameter in theory is a dynamic variable, including the weights that are just dynamically changing on slow timescales in the system, sometimes fast timescales, but everything is one large interconnected nonlinear dynamical system. So what we see this was providing is a future of real-time, adaptive, low-power AI. Thinking of that, cockatiel parrot that's flying through the world, that's distinct from today's AI, which of course we've just had the release of GPT-4, and it's phenomenal what this breakthrough that we're witnessing now in large language models and now applied, transformers applied to almost everything, But you step back, and this technology, this deep learning-based, back propagation-based trained paradigm of AI has its limitations. So on the strength side, it's of course its ability to learn is so far limitless. If you have enough data, it will just absorb it and learn from it, and even generalize in very surprising ways from that. On the other hand, it's incredibly slow learning. You have to have pre-collected all of that data, and then you have to apply this incredibly compute-intensive process to train these. The growth of these model sizes is basically unsustainable given this big hammer we have of backpropagation. Neuromorphic AI, what it offers is adaptation and learning in real time. It won't be the same kind of learning of ingesting terabytes of data, but it will be able to adapt and change its structural properties in real time. It's operating in low power, just like biological brains, able to be deployed into power-constrained form factors, and on the other hand, we're facing challenges, of course, because of the architecture of integrating computing elements in memory, these neurons and the interconnect together, where there's no separate memory that's being accessed. It means that we're limited with the design, the manufacturing tools we have today to just chips sizes that we can build. We can't scale up the workloads using cheap off-chip DRAM. It all has to be done, on chip with a combination of, SRAM or similar state elements and logic. And it's very immature. We're still, we've been doing this for going on 7 years now, and the algorithmic maturity is still, the software maturity is still not where we would like it to be, although there's a lot of progress being made. Okay, so we've we've built a series of chips, the Loihi series, and we've tried to realize some of these properties I've just been speaking about, in a modern state-of-the-art, fabricated chip. This is in, the current version is in the Intel 4 process, our latest process technology. This is, as I'm saying, it has this compute and memory integrated architecture. It has these temporal neuron models. All the communication is happening through spikes or events. You may think of them, small packetized information that's just conveying the fact that a neuron has activated. It has a great support for sparse recurrent networks, unlike traditional AI deep learning chips. It has on-chip learning, so the parameters, the weights in this chip can be modified continuously in time based on programmed learning rules that are operating on locally available information at those synapses. And equally notable is what Loihi does not have. It doesn't have floating point numbers. There's no multiply accumulators. There's no off-chip DRAM. Some of these fundamental properties of today's deep learning chips. We've been able to build chips, systems at small scales, all the way at the USB form factor level that has 1 or 2 chips in them. They communicate natively to neuromorphic cameras, which is a very, complementary technology, which, arose in the 1980s at Caltech from Carver-Mead and is now, seeing commercialization. We've scaled this up to large systems. So we've had 100 million neuron system, and this 5U rack-mounted system has 768 Loihi chips in them. So, we're seeing this great promise of scaling and, exploring all regimes here. And overall, Loihi, as of 2020, when we did a survey of all the results that our users of Loihi have obtained, we have over 150 groups around the world, using this chip, and they've arrived on a number of compelling results, across a lot of different domains. So, visual sensing, pattern recognition and learning inspired by olfactory circuits in nature, robotic arm control, where it can adapt to changes, unforeseen changes in friction or other kinematic changes. Scene understanding, interactive learning, embodied in little humanoid robots, the iCub, and probably the most impressive kind of quantitative gains we've seen is in the domain of optimization, and that's been somewhat of a surprise and very interesting. So things like constraint satisfaction, integer linear programming, quadratic programming, these kind of problems. And here is where we're seeing gains that are approaching this kind of, up to 100 times faster, 1,000 times better, lower energy to solution compared to state-of-the-art solvers for those same problems. So, we have a paper out a few years ago now surveying the Loihi 1 kind of results and looking at this kind of unified view of, the energy gain that Loihi can provide, the solution running on Loihi solving a particular problem compared to conventional solutions running on different architectures, CPUs, GPUs, in some cases, other neuromorphic chips. And then the solution time ratio as the other axis, the conventional solution time compared to the Loihi solution time. So the upper right quadrant here of this chart means that the either the energy and both the energy and the solution time advantage for Loihi is quite significant. And we have, you can see various examples in that regime. On the other hand, in the bottom left corner, we have examples also that don't run so well on Loihi. And that's not so surprising when we dig into some of the results here. But some very clear lessons emerge out of this, that these examples that don't run so well on Loihi are all sort of conventional feed-forward deep neural networks. They don't involve temporal processing. They don't involve recurrence feedback. These kind of features that the neuromorphic architecture clearly can implement well and can benefit from. These conventional feed-forward DNNs don't need that, and so therefore they just don't run that efficiently on the architecture. Now, on the other hand, all of these top right examples are all recurrent networks. So they are using these properties of, quickly converging their solution states through feedback. And it's, these are problems that maybe are not associated with neural networks even. So things like, lasso regression and doing graph search and solving constraint satisfaction problems. But, as we zoom into that top right quadrant, that's actually what we find. This going back to this optimization point, that all of these examples are optimization problems of some kind. What sparse coding, lasso, given a large set of featured dictionary, what's the minimal set that explains the sensory input that it's been presented with? So that's kind of a fundamental observation in brains too, in processing sensory information. There's this kind of sparse coding process that's happening. Things like a graph search too. So, Dijkstra's algorithm, right, conventionally, but using the parallelism of the architecture to be able to find shortest paths in graphs through propagating spike wavefronts. And, of course, that too, on some level it's a biologically relevant problem of planning, either abstract cognitive, thinking, or just very literally planning your route through some environment. We brains have to solve that problem. And including constraints. So if we're trying to, constrain to visit a particular set of waypoints once, now we have an NP complete problem, and that too falls in this category of problems we found Loihi solving, very well. And so that's one key insight that has come from the use of Loihi, is that neuromorphic networks, when well structured, well designed, what they're doing is they're solving their problems. Their inference is really an optimization. They're actively exploring solution states as a dynamical system, compared to a deep neural network, which is computing it receives a vectorized input and it computes in a feed-forward way as a static function a vectorized output. And so that's a fundamental difference in how we think about the workload that we run successfully on a neuromorphic architecture compared to today's paradigm of matrix vectorized, densely vectorized largely feed-forward algorithms. And and then a little more specifically, what's happening here is that these networks are performing a stochastic gradient descent as they're solving these problems, and there's stochasticity in it, which allows them to escape from local minima, but effectively there's some energy function that's been programmed into the weights, or modulated through external stimuli, and then that's shaping this energy landscape, and as you shift it, the system is settling into new equilibrium states that it can do very efficiently and very quickly because of this parallelism, its ability to very rapidly explore different configurations and sparsely jump between these through through the sparse communication. So that is an interesting finding from the research. We've been applying this capability to conventionally formulated optimization problems. So things like quadratic unconstrained binary optimization, QUBO, which can solve problems like maximum independent set problem relevant for wireless communications, many other logistics and planning, and this is popularized from quantum computing because that's the same class of problems that some are targeting with quantum computers. Here we find 3 orders of magnitude outperformance in energy delay product to the best CPU QUBO solvers. We have integer linear programming as applied to train scheduling, working with Deutsche Bahn. We have an example of scheduling their railway networks, comparing that to the state-of-the-art solvers they use operationally. We find 5 orders of magnitude up to it, and very interesting scaling properties as we go to larger and larger problems. This gain to Loihi is getting greater and greater, with these harder problems. Now, there is a caveat here. We weren't as optimal in the solutions in this case compared to the commercial solver that they use. But this is totally first iteration of this, and there's many avenues for improving that optimality and trading off some of the EDP gain for optimality gain. Lots of room there. So it's a space of exploration, not ready to be deployed commercially, but it's certainly promising. Another application we're interested in of this is model predictive control. So, at the heart of model predictive control, which is, state-of-the-art pervasive, control algorithm for robotic systems and other systems, nonlinear complicated systems, is typically a quadratic programming problem. And that too is a class of optimization problems that we have done some work and some success in solving with Loihi. So we see this as, a very kind of standard replacement in this case of just taking a standard QP solver in a conventional control software stack and replacing that with a Loihi acceleration of that. It would have all the same deterministic kind of behavior as a conventional MPC solver. But over time, maybe there'd be more disruptive ways to think about solving robotic control problems. But this is certainly an attractive one in the near term. And going a little further afield, there's actually a big problem we face in the neuromorphic domain of what is the programming model, and anybody who's looked into this field immediately sees that there is no kind of standard way of thinking about designing networks and applications for neuromorphic systems, and once you embrace this perspective of neuromorphic network solving optimization problems, you realize that there's really very little we have that can guide our intuition for how to program these systems. Not even deep learning and the conventional machine learning methods are necessarily suitable. And a class of algorithms called or attractor networks, specifically dynamic neural fields, is an example of where these attractor networks, these optimizing networks, are intentionally kind of engineered so that they hold state variables, and then you can reason about how these state variables, will change, will transition to new states given different sensory input. They can avoid distractors. They can fade away over time. You can tune these kind of properties, which have memory and attention and state transition properties. And of course, this is kind of the building block of what you need to start thinking about, neural state machines and understandable behavior for these systems. These are not very commonly known about in traditional machine learning, AI methods. And that's, quite not surprising given that they just don't run well on CPUs. On today's architectures, you need this ability to optimize and with this great parallelism, implement these kind of attractor dynamics with great speed. And since a CPU doesn't do that very well, there's not much motivation to really explore this type of a paradigm of programming. But a little example of how you might use these is just as a simple kind of object tracking function where you may do some kind of a simple feature extraction, some deep learning based feed forward identification of say fish here in this video. And now you have just this heat map of candidates for fish, and as one gets sufficiently activated, indicating a confidence in that object, now this DNF model, this architecture will latch onto that and hold it, and now as it moves, even in the presence of distractors, it may turn, and the deep learning stage may lose it for a moment. This attractor DNF model will hold on to that state and give it a little bit of persistence to accommodate that kind of noise. So that's an example of how you can start thinking about constructing networks that are quite explainable, understandable in this paradigm. So we are what we regard as, Loihi 1 is in the past, and we're now focused on the next, sort of era where, we think the computational value of this kind of a neuromorphic architecture is very well established. It motivates this interesting new paradigm of cheap continuous optimization, and that is the basic programming primitive that we think in terms of. We've seen many successful learning algorithms. I haven't talked much about that, but that was a big question of whether, so-called local learning rules that are, what's at play in the brain and what we've implemented in Loihi, can be actually harnessed for some, algorithmic good purpose. Given that we still don't know how to scale them up to something like a back propagation algorithm that can really optimize large scale networks. But nevertheless, we have some successful examples of being able to deploy this kind of online learning capability and do, simple associative learning and pattern recognition. And we have a good idea of the suitable application properties of where we can apply this. It's all everything that would match this kind of autonomous flying drone. But you find these in other contexts too, of course. Power constrained, latency constrained, the need to process real-time signals, so video as opposed to static images. The problem structure has to be slowly evolving. So one thing is, once you've embodied a network into this kind of compute memory integrated architecture, you can't just context switch and suddenly solve completely different problems as you can in a shared memory system and you just change your instruction pointer. What you have to do here is you slowly evolve the network. You might be able to swap out sub portions of it, but it does put a constraint on the kind of application you can tackle because of that. Again, we need shallow online learning. If the application calls for it, then that's ideal. And deep learning does apply. So for sure, deep learning is a big part of what we do. We look at it as the offline training component for these neuromorphic systems. We're not trying to implement deep learning on chip. It's more deep learning as a tool off chip to seed the networks so that online they just evolve, basically. It's like. And so now in this, where we are now is our second generation chip, Loihi 2. It improves on Loihi 1 in a bunch of ways. Much faster inter-chip bandwidth in particular, which was a sort of a bottleneck for the Loihi 1 era. We've boosted its capacity, up to 1 million neurons, and thanks to process scaling too, that means we're at a 15 times greater resource density compared to Loihi 1, which is kind of the key pain point for commercialization, I would say, from an economics perspective, besides the research challenges. Also on the software side, we recognize the need for convergence in this field. I mean, although we had lots of interesting results with Loihi 1, they were all developed in silos where the software was not interchangeable. They led to papers, but not a continued line of research where different groups are advancing on, the progress that other groups had made. So we to solve that problem, we've launched an open source project called Lava, which is a new framework for software development designed from the bottom up for these kinds of neuromorphic systems. So involving event-based communication, so message passing, channelized, communication model, communicating sequential processes. If you're familiar with that, that's its foundation. It's multi-paradigm, so we have libraries that support a number of different algorithmic paradigms, so some of which I've talked about here. It allows for behavioral abstraction, so defining behavior at a high level where you don't need to know the nitty-gritty of how to wire up, these networks, and then multi-platform. So it's designed to be portable. You can simulate on CPU. You can then deploy onto a neuromorphic chip. Hopefully, it's portable across different neuromorphic platforms, since clearly we have many generations, to go from here. It's open source, permissive licensing, so we really want the general research community to adopt this and port it to their own research chips and take it forward. And just to show you, make it a little real here. I can't show you physically, but this that is a Loihi chip. It's 32 square meters. The latest form factors we've done here are this kind of stacked 8-chip board, Capella point we call it. That's each one of them is about the size of a credit card. So it's a pretty compact form factor. We're building larger systems too, but that's what we have today. To peer a little bit into Loihi2, I think I haven't really shown any of the details inside the chip, and given the audience of this seminar, maybe that's what you're most interested in. But so you can see the sort of the chip plot here on the right of what Loihi2 looks like. It's a mesh of digital neuromorphic cores. We have 128 of these. They each one of them implement up to 8,000 neurons, so of these stateful neurons, and they communicate then, sparse distributions of these spike messages, as each of these neurons is activated. And it's an asynchronous system. Everything in this chip is asynchronous. Basically, we have an Ethernet interface now, 10 gig Ethernet, and so there's a layer that's synchronous there. But otherwise, it's all asynchronous. Including we have embedded asynchronous RISC-V processors. So that's a realization from the beginning that we need conventional computing. Of course, this does not replace the von Neumann model. And even inside Loihi, we have housekeeping operation management. We have data format conversion that has to be performed and the inputs and the outputs. And for that, we need close embedded, traditional computing. So we have, asynchronously implemented RISC-V processes for that, processors. The whole system is a discretized dynamical system, as I say. The time step, the time is an emergent property here, where through handshaking across these cores, they maintain this kind of digital understanding, a discrete notion of what time the system is operating on. Different cores can get a little out of sync, but the sort of the barrier synchronization, the asynchronous barrier synchronization, is keeping them all sufficiently coherent for the user level behavior. And the asynchrony in the system allows us to operate at variable time steps, but as fast as about 200 nanoseconds now, which would be the increment of time that at its very fastest. And to give you some reference, biologically, these networks, typically we think of a reference time as about 1 millisecond, time step. That's the time scale that these kind of spiking neurons operate in the brain. So we have many orders of magnitude speed up, or several orders of magnitude speed up available in Loihi. So we can, of course, go tackle problems that are not just human timescale, behavioral problems. I think in the interest of time, I won't tell you much more about the internal details of the core here, but it's suffice it to say the internal digital core is not just a von Neumann processor. We don't have a single memory and then a computing structure. We have added programmability in Loihi2, so we have microcode programmed neurons. That was a change from Loihi 1, where we had a pull from the application space, where a diversity of neuron models is really what a lot of applications need, a lot of algorithms need. Internally, we have really a sub array of small SRAM banks, and so there's a great deal of parallelism even inside each of the cores, and the different functional stages of this core is accessing different memory elements depending on what they're processing, and we can redraw the boundaries a little bit based on to get efficient resource sharing across this this fixed memory resource. And so some results with Loihi 2, I guess one, thing we're kind of happy about, even though that's not our primary focus, which should be clear by now, that, we've through some of these improvements in speed and the programmability of Loihi 2 and the fact that we've enhanced the spike messages now to carry graded integer activation values, we've been able to improve Loihi 2's performance on traditional deep neural networks. So, again, not our focus, but it's kind of an essential building block for AI, anything AI today, right? So Loihi 1 had limited ways to implement standard feed-forward DNNs. We have an interesting new model called a sigma delta neuron model that Loihi 2 supports, which is stateful neurons, but otherwise implementing a ReLU, based neural network model. So sparsifying the activity based on, only communicating outputs from a neuron when it's its ReLU evaluation changes by a sufficiently large amount. And with that, we're able to implement things like PilotNet for video steering wheel angle prediction, and achieving some pretty respectable levels of performance and efficiency. Bearing in mind again that this is not what the architecture is designed for, but now in a completely unbatched real-time setting, we're getting reasonable efficiency and performance on that. And another application of that, of this sigma delta neural network model, and really an open problem I'd like to highlight here is applying to audio denoising. So you could see on that video processing PilotNet, we have a temporal inference problem processing video, not just static frames. Audio is another great application domain for neuromorphic chips. It's low dimensional, so it doesn't stress the resources, available in the chips as much as video does. And it's fundamentally, matched to this kind of dynamical system time series processing nature of neuromorphic chips. And we're actually just today or tomorrow, perhaps, we're announcing this challenge for the community to try to solve this problem of state-of-the-art audio denoising. It's a pervasive, ubiquitous function. Every Intel CPU has hardware AI acceleration for this function because it's so commonly used now. And it's relatively high power. It's a compute-intensive workload. And so we think it's a great problem for neuromorphic chips. And we have a Loihi 2 result now that that is actually doing pretty well here. You can see that. I mean, this is a complicated table of results, but it's actually reducing the power, the number of ops by an order of magnitude, model size by more than an order of magnitude, while achieving pretty respectable accuracy results. This is a baseline. We're offering it to the community. This is now a challenge. We want people to, come and use Lava and use Loihi 2 and, try to advance it, in addition to all the other, research directions people are pursuing. But this is an example of a problem we think is ready for, showing really great gains. Okay, I think we're running short on time, so I'll just jump to, the outlook that we see for the commercial value. We do see some opportunities for commercializing the technology. They're maybe not necessarily what you might expect, in the near term. So things like solving optimization problems, that is, potentially fleet routing, logistics types of problems could even be deployed in the data center for that. So that's a relatively mature path, I would say. The algorithms are relatively mature for pursuing that. Probably in the nearest term, there'll be specialized designs that get embedded into SoCs, that avoids exposing the nascent programming model, the immaturity of the software to a large developer base, but really embedding the functions into chips. So sensor integration, for example, directly interfacing with event cameras. You see some of that in the field already. Wireless signal processing. But of course, this kind of as a co-processor, a very efficient, adaptable AI processor that would sit alongside more conventional accelerators and CPUs, bringing these kind of ability to plan and operate in real time, where power and latencies are strong constraints. So yeah, with that, I will end it, and happy to answer questions.
Thank you, Mike. Is this on? Yeah. Okay. Thank you very much. This was a great seminar. So we open this now for questions, and we should do this to this mic so Mike can learn the question. So questions, please. Right.
Thanks for a great talk. My question is, what is the speed compared to the brain?
Well, I mean, it's I would say 1,000 times faster. So, roughly. So the brain, as I was saying, these neuron models, or the biological neurons, operate on about you could say a millisecond time scale, maybe the resolution of what a spike can represent. And in Loihi 2, we can construct networks that operate comfortably at a microsecond level of resolution there. So you could say 1,000 times faster. Obviously, there's caveats and nuances. If you start talking about learning, plasticity, that comes with a performance impact in today in our architecture, degrades it. You could say maybe 10x from that. But yeah, it's certainly considerably faster than biological neural speeds.
More questions. I have a question. So Mike, you described at some point that essentially what is happening is digital calculations, right? You process digital signals in a digital way. Is there a gain to be accrued if we use analog devices that have just the right characteristics that you need? Is this something that would allow you to propel this technology, these concepts further in terms of your energy efficiency?
I mean, I think, yes, if you look in the long, broad view, absolutely. We stick with digital because we see a lot of challenges with analog. First and foremost, from a standpoint of commercialization, you can't pipeline analog. So although you do get these benefits in efficiency, and you can't time multiplex the state and the logic required to implement that analog circuit. So what that means is that we can't use the densest memory technology available. We can't construct a circuit which then through time multiplexing reduces its area impact by that multiplexing factor. So at the transistor level, we're operating at gigahertz speeds in Loihi. And that means that we get, for the logic, we get 1,000 times. So algorithmically, we're operating at a microsecond time scale, or even a millisecond time scale for biological speed. So that's effectively an area reduction we get by pipelining and time multiplexing digital circuits. That's not available to us with analog circuits. So for that reason, from a commercialization standpoint, the economic, the value, digital is, as I see it, just far and away the way to go. But over the long term, through new devices, new manufacturing technology, 3D, analog memory structures, I think there's, some exciting, future there. But we're starting with digital exploring this analog, this architecture algorithmic space as rapidly as we can, which we can do with digital designs. And hopefully that's kind of paving the way, highlighting the path, which is now where we should target the longer term device level analog type of research.
More questions.
Good afternoon, everyone. I just wanted to acknowledge my presence. I'm the college recruitment manager from Intel, and we'll be here throughout the week. And we have a lot of events that are advertised online. So certainly if you're interested in partaking in our Intel Day, it's at 2:30 this afternoon. We have a few other events taking place on Thursday as well. I'll be hanging around after this event if you want to talk with me a little bit. I have some information about career pathways and other information in case you want to upload your resume. So I just wanted to take a moment out of Mike's speaking time to certainly let you know that I'm here.
More questions. We still have time for more questions.
I have a question. I'm from Zoom.
Yep.
This is Shiva. Since you're based on digital electrical implementation, what are the limitations you see? Is power a limiting factor, or is sparsity a limiting factor?
The main limiting factor that from an architectural standpoint, I would say is the learning capabilities. I mean, yeah, the memory resources is definitely a limiting factor, but that's is a more limiting factor, I would say, from a commercialization viability perspective. But that's not a function of digital. That's equally even worse with analog. But the challenge we have compared to a more analog based sort of network memory, synaptic memory implementation is that in order to modify weights, we have to be able to access them with the pre and the post-synaptic state available. And implemented in arrays, dense SRAMs, the best memory technology we have, that's a very challenging problem, how to, in an event-based paradigm, access this single monolithic, sort of memory array. Even though we have many of them, we have to access each one and know exactly the address to kind of update. So that's what I see as kind of the biggest design problem we have, which is a function of being in this time multiplex digital paradigm. In theory, analog implementations wouldn't have that because the state variables themselves can simply evolve and change based on how the array is stimulated. And so that's what I see most attractive as an analog future.
Thank you.
More questions online or in the audience? All right. If not, Mike, thank you again very much for joining us today with this very exciting talk. Thanks.
My pleasure. Thanks for the invitation.